You're watching Practical AI. In this video, we're going to explore Chroma DB, the open-source vector database built for AI native applications. You'll learn what Chroma is, how it fits into an AI workflow, and how to use it in Python to store, search, and retrieve embeddings, the foundation of retrieval-augmented generation. We'll break down real code examples, analyze the output, and end with a quick tour of the official documentation so you can continue learning on your own. Chroma DB is an open-source vector database built for AI native applications. Chroma runs as a server and provides Python and JavaScript client SDKs. You can think of it as a Python package that you can use to store embeddings and associated metadata like a PDF page number, where the original text can be found. In essence, when you convert text into high-dimensional vectors or embeddings and you want to store, index, and query them efficiently, that's where a vector database like Chroma DB comes in. This diagram shows how a Python script, a local LLM, and Chroma DB work together to form a simple retrieval-augmented generation pipeline. Everything starts with the Python script. This is the main control layer of the application. The user enters a query here, which is sent through the script to the rest of the system. The script first connects to Chroma DB. The query is converted into an embedding. That's the vectorization step shown here. Chroma takes that vector and performs similarity search against its stored embeddings. Inside Chroma DB, you can see two main processes: vectorization, which turns text into high-dimensional numeric vectors, and retrieval, which finds the vectors that are most similar in meaning to the user's query. The result of that search is the retrieved data, snippets, documents, or context that relate to what the user asked. That retrieved data flows back into the Python script. The script then constructs a prompt for the language model, combining the user query with the retrieved information from Chroma. Next, the script sends this combined prompt to the LLM, the large language model. The LLM uses both the query and the retrieved data to generate a grounded, context-aware response. The output is then returned to the Python script. This simple loop forms the foundation of retrieval-augmented generation, and Chroma DB makes it possible to add memory and context to your local AI applications. Let's break down this simple Python example and see how Chroma DB works in practice. We start by importing the Chroma DB library and Python's pprint for formatted output. Chroma DB is the vector database we'll use, and pprint just makes the console output easier to read. Next, we initialize a Chroma client. This creates a local instance of the database. By default, it runs in memory, in RAM, so you can test things quickly without setup. You don't need any external server. Chroma runs locally by default. Then, we create or connect to a collection. A collection in Chroma DB is like a table in a relational database. It groups your documents, embeddings, and metadata together. Collections are the main logical grouping of items or records. Think of a collection as a logical container, similar to a table in SQL. We'll use it to store our car descriptions. Now we add entries or records. A record consists of four main components: an embedding vector, numerical vector representations of a document, original text or data associated with the embedding, metadata, structured key value information linked to each document, IDs, unique identifiers for each record. Here, we add three components: an ID, a document, a metadata dictionary. In this example, the documents describe different cars, and the metadata includes brand, fuel type, and color. When we call the collection.add method, Chroma automatically embeds each document using a default sentence transformer model. It stores the embeddings, the text, and the metadata in the collection, ready for semantic search. You can also provide your own embedding function, or even embeddings directly. You can query the collection for similarity search or retrieve records by ID. Each collection is isolated. Queries only search within that specific collection. In short, a collection in Chroma is the container that holds and organizes embeddings, documents, and metadata for a particular dataset or domain. The list collections function simply lists all collections currently in the database, and the collection.count method shows how many records this collection holds. In the output, you can see confirmation that the collection My Collection was created. The line number of records in the collection 5 tells us that all 5 documents were successfully added. Now let's test how semantic search works. We define a search phrase, in this case, family car. Chroma embeds that phrase into the same vector space as the documents and searches for the closest matches. The query method performs that similarity search. We request the two most relevant results and include documents, metadata, and distances. The smaller the distance, the more similar the document's meaning is to our query. The output lists two matching documents, the Nissan Leaf and the Toyota Prius. These make sense. Both are practical, efficient cars, commonly used by families. The numbers in double brackets, around 1.3 and 1.4, are distances in embedding space. Lower values mean higher similarity. Next, metadata filtering. Here, we use the same semantic search, but restrict it to cars that have the color white. The where clause applies a metadata filter before returning results. This is useful when you only want results from a certain category, date range, or any other attribute stored in metadata. The filtered result now contains only one document, the Nissan Leaf, which matches both the search meaning and the metadata condition, color equals white. Finally, let's look at full text search. Instead of using embeddings, we directly search the text of the documents for a specific keyword, in this case engine, using the get method. The $contains operator tells Chroma to return documents whose text includes that word. The output shows three results, the BMW X5, Ford Mustang, and Toyota Prius, each containing the word engine in their document text. At the end, the script prints a structured result object. It contains several fields: documents, the raw text retrieved; embeddings, the numeric vectors representing each document; IDs, the unique record identifiers; includes, and metadatas, details like brand, fuel, and color. Here, you can see three embeddings, each with a 384-dimensional vector. These are the numerical representations Chroma uses internally for similarity calculations. So, in summary, we stored 5 car descriptions with metadata. Chroma automatically embedded and indexed them. We ran semantic, filtered, and full-text searches. And the output clearly shows that Chroma understands meaning, not just exact words. This is the foundation of retrieval-augmented generation, turning plain text into embeddings, searching by meaning, and providing relevant context to your AI model. If you want to dive deeper into Chroma DB beyond what we've covered here, the best place to go is the official documentation at docs.trychroma.com. This site is well-structured and beginner-friendly. It starts with a clear overview and introduction, explaining what Chroma is, how vector databases work, and why they're essential for retrieval-augmented generation and AI-native applications. You'll find an explanation of key concepts like collections, embeddings, and queries, the same building blocks we used in our Python example. It also walks through how Chroma stores data, indexes embeddings, and performs similarity searches. Under the Getting Started section, you'll see installation instructions and your first Hello World example. You can learn how to create a client, add documents, and perform basic searches step by step. So whether you're just starting with Chroma or building a complete local RAG pipeline, the documentation gives you everything, from beginner tutorials to in-depth API details. Now that you understand how Chroma DB works, the next step is simple. Try it yourself. Open your editor, install Chroma, and start experimenting with your own data. Real understanding doesn't come from watching or reading, it comes from doing. Every line you write and every query you test will make the concepts clearer. So dive in, build something small, and let practice turn theory into real skill. Thanks for watching.